Thank you very much for the introduction. I hope my audio is clear. Yeah, and I can see that the presentation is working. So thank you very much for having me. Unfortunately, I could not attend the previous sessions of this entire Citizen Summer Science Camp, but I'm pretty sure the talks must have been really, really interesting. I'll really check them out later on YouTube. And as already been introduced, my name is Anshuman. I work in black holes and wormholes and some other interesting phenomena in gravitational theories, with a special focus on those beyond Einstein's general theory of relativity. But today, rather than going into the specifics of the kind of research that we or us as researchers collaboratively do, I'll talk to you about black holes and what kind of citizen science projects are there that search for black holes or look for properties of black holes, and how this community of citizen scientists can actually help researchers discover black holes or characterize black holes in more detail. So what we'll talk about today basically comprises, we'll basically give a brief introduction about what black holes are. We'll be talking about how these black holes form. We'll talk about why do we study them, why is it necessary to study these exotic and amazing objects. And finally, we'll talk about how citizen scientists can contribute to the study of black holes. Now, I'll be pausing my video so that the audio, the internet doesn't give any issues, but yeah, fine. So let's start. So let us start by talking about the life cycle of stars, because as most of you may or may not know, black holes are objects that are actually most of the times born due to the death of very, very massive stars. So there are different types of stars, and astronomers use different types of methodologies to classify these stars. So mainly this classification of stars are based on their mass, their temperature, and their luminosity. By luminosity, we mean their radiant energy, the light that is emitted from them and how we see it. So let's start with our own sun. Our sun is what we call a main sequence star. It's a fairly common type of star in the entire universe. It's burning hydrogen at its core, and it's converting this hydrogen to helium, and all of the radiant energy we receive here on Earth. It's the source, it's the sustenance for all life forms on Earth as we know it. And then we have more smaller and compact objects such as white dwarfs and neutron stars. These are the kind of objects that are born out of the death of different types of stars. We have massive stars such as the red supergiant stars. These are massive stars that have exhausted the hydrogen content in their cores and are instead burning other elements, most probably starting from helium. Our sun, after approximately 5 billion years, is going to meet the same fate. It is going to expand in size. It is going to exhaust all of its hydrogen, and it will start burning helium at its core. Then we have other massive supergiant stars. There are blue supergiants and there are white supergiants. These are stars that are thousands to millions of times more massive than our own sun. And you'll be surprised to know that some of these stars are so big that they can have a radius that can actually encompass that of our entire solar system, or perhaps more. We have potential candidates for even larger supergiant stars. The proper classification of stars is based on their luminosity and temperature or radiant energy. And as I've already said, our sun falls in one of these classifications. Specifically, it's a G2 type of star. We call it main sequence stars. And then there are class F stars, class G stars, class K stars, and so on and so forth. And these classifications are obtained from what we call the Hertzsprung-Russell diagram, or the HR diagram in astronomy. So it is basically a graph where you plot the temperature and the luminosity of stars. And there is a very, very nice plot that you get, and you can classify stars from O to the lesser radiant luminosity stars based on the behavior that you observe in the Hertzsprung-Russell diagram. So, but what happens to these stars? How do they evolve? So as we know, it stars, and before going into the specifics of black holes, let us study the stellar life cycles. How do these stars evolve? So we know that stars are formed from what we call molecular clouds. So in the universe, the general perception is that the universe is mostly empty. You do not have anything. It's a perfect vacuum. On the contrary, what happens is that there are huge reserves of molecular hydrogen, and in fact other elements as well, although hydrogen is the most abundant one. There are large reserves of molecular hydrogen in the universe inside of galaxies. So what happens is that over time, these molecular clouds, they start collapsing upon themselves. Gravity acts to clump these massive clouds of gas together, and once they attain a particular mass and once they attain a particular temperature, fusion reactions start popping up, right? So that's how a star is born. So once a star is born, depending upon the initial mass of the molecular cloud, the initial mass of what we call the protostar, the path of evolution of stars, it varies. So generally, for low mass stars, such as our sun, we can have the next step of evolution. The star stops burning hydrogen, starts burning helium, and you obtain a red giant. And the red giant finally explodes, and you get what you call a planetary nebula. Or if you have more massive stars, say for example, stars which are around 8 times more massive than our own sun, they, after burning hydrogen, they end up becoming a red supergiant. And these type of stars actually explode. And these huge explosions are called supernovae. And these supernovae lead to some different phenomena. So depending upon the mass of the star that exploded to form a supernova, you can have a remnant supernova cloud, or you can form a neutron star, that is a star that is made of completely of neutrons, or you can even have a black hole. Now, how does this differentiation happen? Which type of supernova explosion leads to a neutron star? Which type of a supernova explosion leads to a black hole? There are different crucial details, which I won't go into now, considering the time constraints. But if any questions arise after the talk, I'll be more than happy to answer. How do specific stars or specific supernova explosions lead to the formation of neutron stars and black holes? Now, another very useful point to note here, the most useful point to note here, is that the most massive of stars, they explode to form supernova that ultimately collapse to form what we call black holes. But what exactly are these black holes? For this purpose, I have borrowed an animation from National Geographic. So what happens is that black holes are compact regions of space-time where the gravitational force is so strong that not even light can escape. This is a popular definition that most of you guys must have encountered in the internet. So you can think of the entire universe as being a space-time continuum. Space and time are intertwined into one particular single object. You can consider itself to be a fabric. Einstein actually explained this to us in much, much detail in his theory of general relativity. And black holes can be considered of as dense or as wells in this space-time continuum. So this gravity curves space-time to such a high degree that nothing that falls into this region can escape, not even light can escape. The boundary that surrounds this black hole is what is known as the event horizon. It's the point of no return. So once anything, if it crosses the event horizon, be it mass, be it energy, be it radiation, be it any form of light, it can never escape. And the central point underlying the entire deep curvature well of the gravitational field, there is a point called the singularity. It's a point that is infinitely small. We don't know what the exact dimensions are. It's a point of infinite density. Now, why do we use the word infinite? Now, infinite doesn't make sense, right? Although you might think of infinity as a very, very huge number, whenever we are talking of physical quantities, infinite doesn't really make sense. Now, physicists, we use the term infinitely small and infinitely dense. You can think of it as physicists being cheaters. We are cheating, right? Why are we cheating? It is because we don't exactly know what happens at the singularity, what happens at the heart of the black hole. And whenever the equations of physics or mathematics break down, we say that we have arrived at a singularity. So a physical singularity exists at the heart of a black hole that is surrounded by an event horizon. Our current models of physics give us very, very good approximation of whatever is happening very, very near the event horizon, very, very near the point of no return. But we don't know for sure what goes on inside of the event horizon. That is something very, very interesting that we can discuss later if somebody wants. But the main point is that if these objects are so massive and so dense that not even light can escape from it, how do we know that such things exist, right? Because these things might be invisible. So as it turns out, black holes were first discussed just 1 year after Albert Einstein proposed his famous theory of gravitation, that is the general theory of relativity. So in general relativity, Einstein said that space and time are combined into one particular object, and the presence of mass or the presence of energy, it generates curvature in the very fabric of space-time. And the black holes, as I've already said, it curves space-time to such a degree that light cannot even escape, right? But there are ways to observe black holes. So we do it right 1 year after, after 1 year after Albert Einstein proposed his theories, there was a very, very famous person called Carl Schwarzschild. He actually developed a solution to the equations of gravity written down by Einstein. And he found that in his solution, any object, if you can squeeze it hard enough, it becomes a black hole. I mean, it becomes an object so dense that the gravity becomes so strong that light cannot escape from it. But it was not until 1971 that scientists got a hint that such things might exist. Now, between this period from 1916 to 1971, people were working on the life cycle of stars, the diagram that I just showed you before. They were trying to figure out how do stars evolve, how do stars die. And some of you might know that an Indian scientist, Sekhar, had a very significant contribution to this study. And until 1971, people started to believe that, yes, exotic objects, wild objects such as black holes may exist in the universe. In 1965, an anomalous X-ray source was detected. People saw a source of light in the night sky that was emitting X-rays at such a high intensity that no currently known form of theory or model could explain how these X-rays were being emitted in the night sky. And in 1971, people actually observed this thing more clearly. The star or the speck of light that you see in your screens is Cygnus X1. It is what we call a binary X-ray source. And this was the first confirmed evidence of a black hole, the kind of radiation that this object was emitting. There was no other way to explain it apart from the presence of a black hole. And nowadays, it is widely accepted that most centers of most galaxies, you know that we live in a galaxy, right? We live in the Milky Way galaxy, and lots of millions and billions of galaxies like our own exist in the universe. Now it is accepted that at the centers of most, if not all of these galaxies, there exist supermassive black holes. By supermassive, I mean they have a mass or they have a weight that is millions of times more massive than that of our own sun. So this is a very, very basic schematic that explains to you what happens in Einstein's theory of gravitation, right? So let me just pull up a pen and highlight you. So the first image here is what we call flat space-time. There is no mass, there is no energy, there is no stars or planets. The space or space-time remains flat. As you introduce mass or energy, as you introduce a star, a planet, or anything very, very heavy into the picture, this fabric gets curved, right? And if you have a mass that is confined to a radius, which we call the Schwarzschild radius, if you can compress a particular mass to a radius given by r equals 2m, if you can compress it that way, you essentially tear a hole into the fabric of space-time itself. And this particular hole, the red highlight that I have shown here, this is the event horizon that I had explained just now. How do we know this structure is accurate? We have actually been able to observe this. So this image you see here is the radio telescope image of the center of a galaxy called Messier 87 or M87. And radio astronomers have indeed verified the structure that I have just shown you in these simple diagrams to be true, right? So in case you see there is a dark halo, this particular dark halo at the center is the event horizon, and this glowing ring of light that you observe surrounding the event horizon is what we call the accretion disk. What this particular thing is, I will explain to you in just a minute. So these kind of evidences tell us for a fact that black holes do indeed exist in the universe, and they're very, very important for the evolution of the universe and for the evolution of galaxies like our own. So this particular picture shows you a schematic of the basic structure of a black hole. This is an artist's impression, mind you. This is not a real photograph, but we have good reasons to believe that this is exactly how astrophysical black holes look like. So essentially, we have something called an accretion disk. Without an accretion disk, we would not be able to see the black hole because the black hole itself is a dark object. It does not emit any light. But what happens is that whenever there is some source of mass near the black hole, say, for example, there is a black hole and there is another star near it, or if there is a black hole and there is a molecular cloud of hydrogen near it, what happens is that the strong gravitational force of the black hole, it starts attracting the matter. And once this matter starts spiraling or orbiting the black hole, this matter is accelerated to such high energies that it starts emitting radiation. By radiation, I mean light. The matter is accelerated to so high velocities that it forms a plasma and it starts emitting light. That is known as the accretion disk. And some of these accreting material, some of this material orbiting the black hole, might be thrown out of the plane of the black hole at very, very high speeds. This is what we call a relativistic jet. There is also a very interesting region called the photon sphere near the black hole, which we have also been able to verify. If anyone is interested in knowing this, we can discuss this at the end of the talk. And this very, very fine boundary that you see here is the event horizon. We call it the event horizon because events that are happening below the event horizon after crossing the event horizon, as I have said, we do not know what's happening there. We have no known method to observe whatever is going on beyond the event horizon. And at the heart of the event horizon lies the singularity of the black hole. That is where all known laws of physics break down, and we are still trying to figure out what happens at the centers of such massive black holes. Now, why do we study black holes? Black holes are so compact objects. Okay, thanks. So why do we study black holes? First of all, there is a very, very big conundrum, right? Black holes are so complicated objects because black holes are formed from dying stars. Stars may be of different types, different kinds. But even after all of these complexities, you will be surprised to learn that black holes are very, very simple objects in the sense that they can be characterized only by three properties. The first property is their mass or the weight. What is the weight of the black hole? The second property is the angular momentum. Angular momentum is a way of understanding how the black hole is spinning about its axis. And there is something called charge, but most of the times we ignore the charge. And all of these phenomenon are combined into a very, very funny named theorem in physics. We call it the black hole no-hair theorem. We want to verify if this is true because scientists want to know that black holes are so complicated objects, they do not emit light, we cannot observe them, but how can they be so simple, right? So we want to verify the no-hair theorem. That is one of the reasons we study black holes. The second reason is more intriguing. Are there primordial black holes? By the word primordial, I mean black holes that are existing at the very, very early stages of the universe, at the dawn of the universe. So we have good theoretical models that tell us that when the universe was born, some special type of black holes were also born that were not born due to the death of stars, but due to different reasons. And it is of much, much importance to fundamental physics to understand if primordial black holes exist. The next reason we study black holes is to understand how supermassive black holes form, right? Because the type of black hole formation that I explained to you, these are what we call stellar black holes. Stellar meaning arising from stars. We know for a fact how black holes are born out of stars, but we do not know how supermassive black holes are formed. We know that supermassive black holes are found at the centers of most galaxies in the universe, but currently we do not have any concrete way of understanding how do these supermassive black holes form or born in the first place, right? Finally, there is a very, very important theorem put forward by Sir Roger Penrose, that says that singularities cannot exist in the universe without an event horizon. This might be a bit complicated to understand. If anybody has a question, I'll answer it later. And the final and most intriguing reason we study black holes is that we can test Einstein's theory of general relativity using black holes. This is the last reason, is the primary reason that I myself study black holes in my own research. It is because we can test Einstein's theory. Now, why do you need to test Einstein's theory? Although Einstein's theory is the most accurate theory of gravity, there are two very, very big shortcomings to Einstein's theory. The first shortcoming is that Einstein's theory of gravity is what we call a classical theory. So you might have heard of a theory called quantum mechanics. Those of you who have seen Marvel movies might have heard of the word quantum realm in the Ant-Man movies or in the Avengers movies. Of course, these things are not real, but the underlying concepts are actually real physical concepts, in the sense that there is a theory called quantum mechanics that explains the behavior of very, very small particles. And general relativity tells you the behavior of very, very big particles, like the sun, like the star. General relativity does not have a quantum theory. The second big problem of Einstein's general relativity theory is that it does not account for some observations in the universe. We know for a fact that the universe is expanding at an accelerating rate, and Einstein's theory of relativity has no way to prove that, to show how this is happening, right? So this is why theoretical physicists like myself, what we do is that we propose modifications to Einstein's theory. We propose physically well-grounded ways in which you can test, in which you can include different parameters in a theory and see if they can overcome the shortcomings of Einstein's theory, right? And as it turns out, black holes are a very, very interesting ground to test for modifications of gravity. Now, why is that the case? Because all of these different modifications to gravitational theories that we can have, they will also give you black holes. The main question that we ask is, how are these black holes different from the ones that we observe in the universe? So these are the main reasons that I can think of why people study black holes in the first place. And we have used different kinds of methods and different kinds of techniques to actually study black holes, and we have concrete experimental evidences that show us the different types of black holes do exist in the universe. Now, how is it that scientists study black holes? That is something very, very important that you should know, right? How do scientists study black holes in the first place? So the first perspective is a purely theoretical perspective. So the purely theoretical perspective involves, first of all, writing down new solutions to the equations of gravity, right? So you can take Einstein's theory and you can write solutions, or you can make solutions that give you black holes, or you can modify Einstein's theory of gravity and then you can see what kind of black hole solutions that you get. The second approach involves deriving meaningful results for experimentalists to verify and use. So some of you might be aware of gravitational wave astronomy and fields like radio astronomy. What these experimentalists do is that they take their observations and they try to correlate their observations with theoretical results. So what theoretical physicists do is that they derive meaningful results regarding black holes, and experimentalists can then use these results to compare what they're seeing in observations. Yeah, can we please mute the microphones of some of the participants? It becomes a bit disturbing to continue this way. Yeah, thank you very much. So the second perspective from which black holes are studied is the observational perspective, right? So there are different observational perspectives. The first one is using X-ray astronomy. In X-ray astronomy, you try to measure or characterize the different X-rays that are emitted from different parts of the universe. And the second approach is using radio astronomy. That is when you look at different kinds of radio waves being emitted from across the universe. The third one is a very, very new field starting from 2015. We call it the gravitational wave astronomy. I'll explain to you what gravitational waves are in just a moment, so bear with me for the time being. The next way we study black holes experimentally is using gravitational lensing. I'll explain what gravitational lensing is too in a short while. And there are other avenues for observations that also exist. For example, scientists, what they do, they look at the orbits of stars that are orbiting very, very close to the supermassive black hole at the center of our own galaxy. And by calculating and predicting the orbits of such stars, scientists can actually measure the properties of the supermassive black holes that is present at the heart of our own Milky Way galaxy. So there are some areas where citizen scientists can contribute to the study of black holes. The particular areas that I will be highlighting today involve gravitational wave astronomy and gravitational lensing. And there are two very, very interesting citizen science projects that you will talk that we can talk about with that, sorry, that we will talk about today where you can contribute. The first one is called G-Witch Hunters. I will tell you what these words mean. And the second one is called Black Hole Hunters. So let us talk a bit about the fundamental principles of detecting black holes using gravitational wave astronomy and using gravitational lensing. And then we will directly move on to these projects and we will see, we'll have a hands-on demonstration of how you can actually contribute to this field using these particular two projects. So let us talk about G-Witch Hunters and what is the principle behind this project and what are the principles using which gravitational waves are detected. So gravitational waves are actually ripples in the fabric of space-time, right? What do I mean by ripples in the fabric of space-time is that whenever you throw a stone into a pond, you see that waves are being emitted, right? Similar thing happens in space-time itself. So whenever gravity becomes very, very violent, say for example, when two neutron stars collide, or when two black holes collide, or when two very, very massive, or when a very, very massive object collates on itself, these ripples or waves are created in the very fabric of space-time. So this is a simulation that I have adopted from the Simulating Extreme Spacetimes collaboration that actually shows you how two black holes orbit each other during a process called coalescence, and they finally, their orbits get shorter and shorter, they approach each other and they finally merge. And the signal, the blue signal changing or evolving that you see below the main animation, it actually gives you the profile of this signal that we can measure here on Earth as this entire process evolves. And the color gradients that you see in the map, the blue color tells you less space-time curvature, the green color tells you about a higher curvature, and as the color changes to red, the curvature changes more. As these black holes, they approach each other, they finally approach a stage where they can no longer stay separate and they merge into one. This exact slowing down point is where they start merging into one black hole. These two black holes pull each other so hard that their event horizons merge, and the excess energy is actually radiated off as gravitational waves. The pink ripples, analogous to the ripples in a pond that you see in the animation, are actually gravitational waves that we can measure using gravitational wave detectors here on Earth. Now, how do you detect gravitational waves? What is the principle behind the detection of gravitational waves? So as I've already said, gravitational waves are distortions or disturbances in the fabric of space-time caused by violent seismic events, such as the collision of black holes or neutron stars. And the main detection principle uses the principles of interferometry. So those of you who have studied higher secondary or BSc level physics might be aware of an instrument called the Michelson interferometer. And that is the very basic principle that is used in big detectors like LIGO. LIGO stands for Laser Interferometric Gravitational Wave Observatory. So the principle behind GW detection is that a passing gravitational wave will cause a change between the distance between 2 points in space, because space-time itself is wobbling like ripples in a pond, right? Interferometers are the most sensitive type of gravitational wave detectors. Interferometers, as the name suggests, can detect interference. Interference means the ways in which two different rays of lights can combine to give you bright spots or dark spots. If you have a doubt about this, I'll explain in more detail. Another approach that people use to detect gravitational waves are what we call pulsar timing arrays. Pulsars are very, very energetic sources of radiation in the sky that pulsate at a given particular time period, which is always constant. When a gravitational wave passes through a pulsar, it actually changes the time period a little bit, and we can actually measure it using telescopes here on Earth. So one of the big challenges in gravitational wave detection is the presence of noise. By noise, I mean disturbances in the signal that can actually hamper the result that you're trying to observe. So in the figure that you see here, the figure explains the very, very basic schematic of the laser interferometric gravitational wave detectors that we use. So what you have is that you have a laser source that emits lasers, and you have an optical device called a beam splitter, which actually splits this laser wave into two components. One of these components is sent into one direction, one of these components is sent into another direction, and there are reflecting mirrors at both ends that reflect this light, which is in the end detected by what we call a detector. The specific type of detector that we use is photodiodes. Now, what happens as gravitational wave passes is that the detector detects something different. So lasers are a monochromatic light source. They produce interference. The beam splitter works in such a way that something called destructive interference occurs, and whenever there is normal operation of the device, the detector will not detect any photons, meaning the detector will not see any light. But whenever a gravitational wave passes, either through the north arm or through the west arm, through any of the arms, it changes the stretching, it changes the length of the arms. And when the length of the arm is changed, the propagation of light through that arm changes. As a result, you get what we call constructive interference, and as a result, an interference pattern is formed, which is detected by the photodiode. So this is the basic principle of detection of gravitational waves. But the most important challenge in detecting gravitational waves is noise, because you might not know, but the detection of gravitational waves is the most sensitive experiment conducted in the history of modern science. So it is sensitive to very, very tiny fluctuations. Say, for example, you know that the Earth experiences earthquakes. What you might not know is that even when we are not experiencing earthquakes, there are disturbances below the Earth's surface that are continuously causing seismic waves to occur. Seismic waves are actually disturbances beneath the Earth's core, and such tiny disturbances, which you and I cannot feel, even such disturbances can affect this experiment. The presence of a vibrating mobile phone 2 rooms away can actually affect this experiment as well. So as you see, this experiment is highly sensitive to noise, and as citizen scientists, you can contribute to understanding what kind of noises are present in gravitational wave signals, and using the analysis that you can do, scientists can actually develop models that can better identify noise in gravitational wave data. Meaning, if there is a polluted gravitational wave data full of noise, there are different methods using which scientists can filter out the noise and actually look for the exact signal of gravitational waves that we want to discover. And you as citizen scientists can actually contribute to identifying noise in gravitational wave signals, using which scientists can build more accurate models for signal detection. So noise in gravitational wave detectors arises from different kinds of sources. This quantum noise that arises from the inherent uncertainty of the photons comprising the laser. There's thermal noise, meaning even by the way, these apparatuses are maintained at very, very low temperatures. Even at such low temperatures, tiny fluctuations in heat can create thermal noise. There can be environmental noise, say, for example, seismic noise, I have already talked about. There can be other sources of noise. The laser device might itself be a source of noise. The control apparatus that you use, the different electronics that you use in all of the equipment in this detector, they might contribute to a noise. And all of these things, they actually pollute the gravitational wave signals. So gravitational wave signals are actually obtained as spectrograms. Now, mind you, spectrograms are not the only way we measure gravitational wave signals, but this is one of the most important ways in which we see and measure gravitational wave signals. And the light-colored regions that you see in this plot, the light-colored region specifically in this plot is shown as yellow. These are actually noise signals. So noise signals have specific patterns. By the way, if you don't understand what a spectrogram is, a spectrogram is actually a plot, or it's a graph that shows you a collection of frequencies and how these frequencies are changing over time. This kind of spectrograms are not only used in gravitational wave detectors, it is crucial for different fields of science. But in gravitational wave physics, it is one of the most important methods using which we can actually identify proper gravitational wave signals. But then you might ask me, sir, how does the actual gravitational wave signal looks if the noise signal looks like this? So actual gravitational wave signals look like this. There is a reason that look like this. The uprising in both of these plots below that you see, it's actually indicative of the ring down and merger phase, the mutual rotation of the black holes and then collapsing into one, the animation that I just showed you. It directly corresponds to the spectrographic profile that you see in the plots below. The citizen science project today, which we are going to talk about, actually tells you how to identify different kinds of noises and how to help scientists better filter for these noises. Next, let us talk about the second citizen science project which we will be discussing today, which is black hole hunters. And this is based on the principle of what we call the transit method in astronomy. Let us talk very briefly about what that is. So the most effective method to detect exoplanets or extrasolar planets is the transit method. What I mean by extrasolar planets is planets that orbit stars other than our own sun. So how transit basically occurs is that, so you have light that is coming from a star, and whenever an exoplanet passes in front of the host star, a dimming in the particular light profile occurs. And as it turns out, this dimming can be observed in light curves. So let me quickly explain what this is. So you see that this is the host star, and it is emitting some kind of light, right? The constant light from the host star we can see using our telescopes. But whenever a planet, or for that matter any object, it passes in front of the star, there is the certain dip in the light profile that we are seeing. So the light is blocked by the planet, and the light intensity drops, and it remains again, and it remains constant again, right? So if we see such periodic dips, we can be pretty sure that the star that we are observing actually has a planet that is orbiting it. And using this transit method, we can determine very, very important properties such as the characteristics of the exoplanet, its size, its composition, whether it is rocky, whether it is gassy. We can even use spectrographic techniques to measure the composition of its atmosphere. We can detect whether there is water vapor present in it, whether there is liquid water present in it, lots of different things. And out of the many, many extrasolar planets that we have discovered till date, most of them are actually discovered using this transit method. But as it turns out, this transit method for exoplanet discovery can also be used to detect black holes. How that happens is that black holes can actually lead us to a phenomenon called gravitational lensing. So what happens is that black holes have such a high gravity that they curve and distort the fabric of space-time in such a manner that light actually bends around the black hole. Let us see a very, very brief schematic of how that happens. So if you see this animation, there is light that is coming from a cluster of galaxies, and in between there is a black hole present, and the black hole is curving space-time such that the light from the galaxies that are behind the black hole, it is curved, it is distorted, and it is magnified. Sometimes we call it, this entire phenomenon, gravitational lensing. So what happens in gravitational lensing is that sometimes whenever there is a black hole that is passing in front of a star, the black hole gravitational lensing can actually magnify and amplify the star's light and direct it to our planet. So you see this graph has an opposite behavior to that for planets, right? For planets, the behavior was like this, and for black holes, the behavior is ulta. Why is this behavior reversed? Because, as I have just said, the gravitational lensing, whenever a black hole passes through in front of a star, the light from the star is magnified and correctly focused to our plane of vision from Earth, and we can then say for sure that, okay, a black hole perhaps exists and that is orbiting around another star. Now, one very important assumption in this scenario is that we assume that the black hole is located sufficiently far away from its companion star so that it cannot accrete the matter, because if it starts accreting matter, the black hole itself will start blowing up, and then we have to use different techniques to find the black hole. Fine. So in this second black hole citizen science project called Black Hole Hunters, what you can do is that you can look for light profiles from the transiting exoplanet survey satellite, the TESS satellite, and you can look for peaks like this in light profiles detected by the satellite, and you can help scientists identify if black holes are present. So this is the end of the formal part of the talk. Let us now try to see a demonstration of how you as citizen scientists using your mobile devices, your laptops or your iPads can be a part of the scientific community and contribute to the detection of black holes. So I'll stop presenting and then I'll go to the websites and let's see how this thing is done. Let us start with the first project. The URL of the first project, it is hosted by Zooniverse, by the way, which is basically a very, very big citizen science platform for different kind of experiments. I hope these links will be provided to you at the end of the talk by the organizers. So what you can do is that you can go to this website, you can create an account, you can go to register and you can create an account. But for the time being, I'll not create an account and I'll just go and show you how you can use your mobiles and laptops to understand noise data in gravitational wave signals. So let us first go to the basic tutorial, which is Playground. It explains to you what a glitch is. So at this very first level, you will be taught about glitches. So glitches are what we call transient noise in physics. Transient noise is basically noise that arises from various different kind of sources. It's the most common type of noise, and it pollutes gravitational wave signals significantly. And this tutorial actually tells you what are the different types of transient noise patterns that you see in gravitational wave data and how to identify them. There is a field guide on the right, as you can already see. It tells you what are the different kind or shapes of data that, noise that you can see. And what you can do here is that you can first try to identify what are the basic types of noises. So let's start identifying, right? So let us try to guess, right? So this is a spectrogram. So there is frequency on this axis and time on the x-axis. And the color graph, it shows you the normalized energy. The lighter regions, they actually correspond to noise or real signals. So there are different kinds of noise. The first kind is blip, that looks like, the best way to put it would be a candle flame. There's the koi fish pattern, which looks like a koi fish, if you know what that is. There's a scattered light pattern that looks basically like whenever you're, say, shining a torchlight at a pool of water or at a bucket of water, right? And then there is an option to say that I do not see anything, or you can say that this is another kind of noise. So this, by looking at it, I can guess that it is perhaps scattered light or perhaps another source of noise. I know for sure there is noise because there is light colored regions here, right? Let us click others and see if this is accurate. It says correct. We have correctly identified the glitch class. Let's try another example. Okay, so here I can see in this particular region that there is a lightly colored region that is scattered. It looks like what would happen if I shine a torchlight on a muddy pond of water, right? So I think this is a source of scattered light noise. Let us click on this and click done. See, we have correctly identified the glitch class. So you can keep on practicing for different kind of profiles. And once you are confident that, okay, I have learned to identify what are the different kinds of noise patterns present in gravitational wave data, then finally what you can do is that you can go to the main part of the project. Let us go to the main part of the project, where you will actually look at real data. So all of this data that we were looking at right now, these are what we call synthetic data, meaning these are generated by computers. These are not actual data. Now we'll go to the more advanced task. So what you can do in this class is that, first of all, you can identify if there is a source of, if there is noise that is happening. This first part is actually analogous to, it is the same as what I had just shown you in the simple experiment. And the main thing that is happening here is that this experiment, it gives you other spectrograms. These other spectrograms are actually spectrograms that are obtained from different components in the gravitational wave detector. Say, for example, this one is the spectrogram from the western arm. This one is the differential arm length, meaning the difference between the lengths of the arms. This is an accelerometer, which is a seismic sensor. This is a waveguide, which we call the IMC. And what you can do is that if there is a source of noise, you can highlight it here. And then what you need to do is you need to highlight regions in the other spectrograms that contains a feature that is similar to this particular little feature. So this type of cross-validation actually gives scientists a concrete idea to make sure that, okay, this is actually a noise source and not a signal of interest that we are missing out. So let us first try to figure out what type of noise this is. So this perhaps might be a scattered noise or an extremely loud noise. Let us try going with scattered light and go to the next task. What we now need to do is that we need to draw a rectangle where we think that the noise exists. So this is the region where the noise exists. So let me draw a rectangle on it. I'll click next. And now what I need to do is that I need to go to the other spectrograms and I need to look for a feature that resembles the triangular area that we have highlighted here. And if any of these graphs contain a region that looks like this, scientists can know for sure that, okay, one of these particular instruments is the source of the noise. For example, I can click on this region here the IMC plot, and I can click on this region here, the differential arm length, and I can click done. So you see that this particular little feature, it is not present in the Western arm or in the accelerometer, right? What this tells scientists is that this particular noise, this light colored region that we observed in the first graph in the entire gravitational wave data, perhaps this noise or this disturbance is arising from the IMC or the differential arm length. So we can click on done. So once we click on done, another new source will be loaded for us. And this is real data, by the way, that you're working with. You can repeat the same process, and all of these data are stored by scientists. And later on, scientists use whatever annotations that you have done to develop new models that can actually filter noise from gravitational wave data so that we can have more precise and clear gravitational wave signals. So this is the first citizen science project which we want you to be a part of. I will now go on and talk about the second project, which is the black hole hunters. The second project that we'll be talking about is Black Hole Hunters. This is the URL. It will be provided to you at the end of the talk. And as I have explained before, it uses light curves, and it looks for peaks in light curves that are indicative of gravitational lensing, which in turn are indicative of a black hole passing in front of a companion star. So let us start by working with synthetic data. So this is the training level. Let us practice detecting light curves. So what you are essentially looking for is peaks. This is a light curve. These white points are measured data points. These red points are measured data points with a wider frequency distribution. And you're looking for peaks that look like this. So you might see a peak like this, and you might say that, okay, this might be a good signal. This might be indicative of a black hole passing in front of a star. Let us click done and see. There's no light passing right. This is not quite right. There is no lensing peak. Although it appears as a peak, there is no lensing, right? So this is why you work with the toy model first. You keep on practicing, and then you see if there is any curves, right? So looking at this curve, I can see that there are no peaks like the graph that I showed you. So I'll just simply click done because there was no peak. This appears to be a peak here. I can use my mouse and I can drag and click and see if this is a peak. There is a peak, right? So this is a simulated lensing event, and there was a peak that was situated here. Let us keep on classifying. This is a clear example of a peak. It is exactly looking like the graph that I showed you in the presentation, right? So you can highlight this and click done. This is also correct. So you can keep on practicing. So at least practice this for half an hour straight if you want to get more and more accurate. And once you're done doing this, you can actually go back to the main page. Now, again, I strongly advise that you register and create an account so that your progress is safe. So that anytime you make a meaningful contribution using real data, you actually know that your contributions are being acknowledged properly. So now you can go to real light curve data, and you can start classifying data from the TESS telescope, right? So you are looking for a graph, a light plot that has a peak that looks like this. This type of peaks that are spaced close together, these are not actually correct. These are actually arising due to noise sources again. And what you're essentially looking for is a peak that has at least one red dot in addition to white dots, right? So this looks like a very, very messy data. I don't think there are any peaks that exist here, so I'm just clicking done. So this looks like there is a peak that's existing in this particular little region, although it might not be the case because it doesn't look really accurate. So I'll just click done. Now, mind you, you're working with real satellite data now. In this light curve, you see two peak regions that are placed very, very close together. So this is not very, very accurate, right? Because we know that we have just shown you in the demonstration that peaks placed very, very close together might not be actual signals coming from gravitational lensing events. There seems to be a very, very nice peak here with at least one red dot in the region. So let us highlight this. And in this manner, what you can do is that you can keep on highlighting different peaks. You can keep on analyzing satellite data. And once you have created your own account, all of your statistics, all of your classifications will be shown here. And anytime you make a meaningful contribution to the project, it will be highlighted to you. And lots of citizen scientists have actually contributed to meaningful scientific publications, really, really good scientific publications using projects such as these. So US citizens, without amassing a very, very massive knowledge of physics, can actually contribute to detecting black holes in the universe. This concludes the formal part of my talk. If there is any questions or any doubts, I'll be more than happy to answer them. Thank you. So yeah, I see a question in the chat box. Yeah, gravity spy. Okay. That's also a very good thing. Is there any citizen science group which is working on this project? There are lots actually. You can actually work on this individually. And if you go on to the publication side, I mean, I have stopped presenting that particular page. But if you go on to the publication side, you can actually see different groups that are contributing to these projects. There is another question. So you mentioned about photon sphere. Could you please elaborate? Yeah, definitely. So what happens is that whenever you look at the Schwarzschild solution, the solution to the Einstein's equation of gravity that gives you black holes, there is a particular radius. That radius depends upon the mass of the black hole that you are talking about. So photons, as you know, are particles of light. They are quantas of light, right? So light that is traversing and falling into the black hole, once it reaches that critical horizon, which we call the photon sphere, light actually bends around itself. It starts revolving in circular loops around the black hole, and the prevailing, popular science metaphor for this is that if you could stand at this particular location, you could see the back of your head, because the light that is traveling from the back of your head, it would travel in a loop in a circle and end up in front of you. So the photon sphere is a region around the black hole. It's a critical radius around the black hole where photons get trapped into stable circular orbits, and they always keep on orbiting there. So that is what the photon sphere is. Is there any minimum threshold for initiating gravitational ripples? Threshold for mass of body? As it turns out, gravitational waves, for them to be measurable at least, you need very, very massive coalescence events happening. For instance, you can observe, or you can at least theorize gravitational waves arising from the collapse of very, very massive stars, right? And there is a mass limit regarding what kind of inspirals or what kind of what are the masses of the two objects that are revolving each other in order for us to see a gravitational wave events. So there is a very, very prevailing notion that generally we observe gravitational wave events whenever there is a mass difference, right? There is a very, very huge object and there is a very, very small object they're coalescing. This is one limit or bound. There is also a very, very important topic that we discuss in the gravitational wave community, which we call uh, equal mass ratio in spirals. That is very, very difficult to detect. So there is no particular numerical value using which you can actually detect gravitational waves. Gravitational waves are emitted due to any violent, strong gravitational effects that are happening in space-time. But what type of gravitational waves we can detect, that actually depends upon the sensitivity of our instruments and the mass of the coalescing or collapsing objects that we are observing. Yeah, these are the questions that I had seen in the chat box until now. Yeah, please feel free to ask away if there are any more questions.
Okay. Hello. It's an honor to be here. Thank you for having me. And I think I'm going to change a bit my initial plan based in what Dr. Anshuman was speaking of. Sorry if I mispronounced that. Since he was speaking about black holes, one of the projects I am currently part of the science team is Bush Chasers. So I think I'm going to change a bit my initial order to speak about the project and maybe start with that. Uh, oh, yeah. So Soban, that was the person that asked me for the participate in the call, asked me a easy task, but at the same time a bit difficult since I participate in several projects, and every project is kind of different in a way, while still be similar because all the projects are in Universe. So basically, how the projects work, how you can participate, what you do in every project, and how can you contribute in them. So I ended settling by not doing a PowerPoint presentation and just use the live site since I helped to create most of them and all the explanation are there. So let me start the screen sharing. Where Yes, you are there. I need my screen one. Yes. And hello. Come on, hello. Yes, looks like it's sharing. It's sharing correctly, right? So thank you. So every project I'm going
Yes,
to
sir.
speak about is, sorry, somebody has a question? Oh, I was hearing a noise. First, every project I'm going to talk about is currently in Universe, except for the last one I'm going to talk that is in review on Planet Patrol is in a weird space right now, but every project is in Universe right now, and you can search for them. Even the Soban, I'm going to give the link to Soban later in case he want to share it. But every project is present in Universe, so you can just jump in like. The doctor was presenting before when speaking about the gravity waves projects. I mentioned Gravity Spy because that is another project that deal with that, but yeah, I don't have exactly the time to work on also. Gravity Spy is just kind of there in the back burner. So, but why I am going to speak about Chaser first? Because it ties nicely with the black holes thing that we were talking about before. We were speaking about gravity waves that are kind of the weaker side or result of a black hole, while gamma ray burst, that is the phenomenon that occupies Chaser, is in kind of the opposite side. Chaser wants to deal with the more energetic explosions that we know in the universe currently, that are gamma ray bursts. And one of the origins for these phenomena are, for example, the formation of a black hole when a massive star that also the doctor was explaining in his presentation at the start of the call, that can emit massive wave of energy, and one of the possible results are the gamma rays uh, jets, like we see here. And another origin for gamma ray bursts are when a neutron star and a black hole merge, or two neutron stars also do the same. So I'm going to speak about a bit about this project a bit, so we can kind of round up the black hole theme and later move on to another astronomical subjects. So, like the doctor was telling before, black holes can be a tricky thing, and they are a phenomenon that are not entirely understood now. And not only the mechanisms, but the results, the energy that are emitted in the process, how you can track them. Is everything in that subject of astronomy is, I will not say in a newborn state, but is constantly evolving because it's a relatively new field still. The improvements are constant in every time we discover something fundamental about the mechanisms of how they work. So in the case of bird chasers, the idea is to understand better this very energetic result of a black hole colliding, or a massive supernova when it collapses and is going to end in a black hole. And we are trying to search a way to understand better the morphology of the burst, how they behave in time, and the idea behind that is to understand better the mechanism behind it, because we kind of know how they originate, but we are not entirely sure the how. So that is the interesting thing about it. For example, here we are. The audio doesn't matter much, and you can find this in YouTube. It's part of NASA. How gamma ray bursts can result from a collapsing star. You can see that start to emit a jet, and that always happens in two ways. So you have two jets, and believe me, you don't want to be in the near stellar neighborhood when that happens, because yes, can be very bad for two things like keeping your ozone layer, for example. So luckily, we are not in risk to having any of those very close by. So there you can see how a gamma ray burst can start and be detected. Of course, these one are much easier to detect compared to the gravitational wave. A gravitational wave are very, very, very tricky to detect. That was the reason when back in 2017, the first confirmed detection was something so big for the working models, because until that point, all that was just a theory. While this is more, it's a bit more easy to grab with instruments. And here we have another example when two neutron stars, you can imagine one of those being a black hole, do a merging, and you have the burst as a result. Uh, what we can equal this with the gamma, with the gravitational wave, that these are transient events. So at the same way that the gravitational waves, you have to capture the event in the moment it's happening, because it's not going to last very much. Aside that in this case is so high energy that you can grab it more easily compared with the gravitational waves. But they share the same characteristics. There are transient events. You have to grab it when they happen, and you are going to analyze the data you have. You are not going to be observing a live event like when maybe you do in a exoplanet transit, because yes, once you see the event and once you record the event, you are going to analyze the result of that, but the event already happened. So in the case of gamma ray bursts, our interest is to not only grab the events but understand them. Oh, sorry, to start the. You can see here how many events, for example, were captured for the Swiss observatory from his start in 24 to the current days. So you start to see why in citizen science we need the help from the public, because there are just simply too many data points, too many interesting subjects, too many phenomena to be properly studied by a reduced science teams in a university, in an observatory, in an institution. You need the public because otherwise there is no way to deal with the data. And once a new observatory start to come online, we are going to have even more and more and more of that problem. So we really need the public to participate. So, and that was just only a bit. So, okay, how you work in this project? This project actually have two sections, and you can, well, no currently because one of the workflows is complete. Yes, this is complete. But you can jump in and see we are going to have more data in that section soon. You can work in two sections of the project in two different ways. To see the shapes of the pulse of the gamma rays, this is what we call a light curve from a gamma ray burst. As we analyze the shape, and we analyze if there is a pulse in the light curve or not, because sometimes computers just get confused and they mark you background noise as a possible real phenomenon, and you have to deal with that. And that's happened with every astronomy project. You have false positive, what is called. So I'm going to go to the, yeah, I'm going to the practice. That is my recommendation to start, where to start, aside reading the about page, the FAQ, and so on. You can see that it's asking you, and you can have the tutorial also, how to classify the shapes and where is a pulse to difference from the noise and for a possible false positive. So I'm going to kind of go quickly about this because we have several projects to talk about. Again, you can just go to the pages and immerse yourself and your own pace. Get started in whatever project you get more interested in, because maybe for some people light curves are not so interesting. They prefer to see more astronomical image when you see the stars. So Lockless Universe have you covering that. You can find something that's going to interest you for sure. For example, galaxies for me are kind of boring. I know people love galaxies, but I prefer to deal with stars and things like that. So yes, in this part of the project, you can see, you can mark if there is a pulse, there is a noise, or if you cannot tell because there are some images that are kind of ambiguous. Don't worry to be wrong. I'm going to mark everything, to mark just something to move. For example, and give you the feedback, and there is a pulse. Almost all the counts in the red circle are about zero, and they go to explanation why there is a pulse there and not just noise. But it's hard to tell, and people we need people to help us to be sure about that and to better improve the how the computers classify that. So the automatic data gathering process that we use initially to graph the data are better. So we have to clean less garbage data before putting science citizen science project together. Remember, this should be a pulse. And I give you the feedback in the tutorial. You got it. This is a pulse. Despite some small noise fluctuation, and give you the explanation how you can there differentiate the noise from the actual pulse and how to familiarize with the form of the light curve. This should be noise. Let me it's a pulse. You can be wrong. It's so noisy that you can be wrong sometimes. So this is a pulse, and so on and so forth. The other workflow you have here, you have to go back and option here, are the shapes in the case of the gamma rays light curve, because that also tells a lot about the origin of the pulse, how the explosion went, maybe what it generated. It was a supernova, it was a black hole, it was a neutron star merging, whatever. So the structure is also very important for that. So we can have simple pools, more things more complex, like we were saying before. Also, this project have a field guide where we detail all that, the different, what is a pulse, what is the blue region that you may be wondering, um, how to deal with marking that, and so forth and so on. There is a lot, and it's very hard to compress in a, let's say, 1 hour presentation. So feel free to jump to the projects, ask about every project have this section called talk, where you can ask about the science or about a particular subject we are dealing with. So yes, here we have in the tutorial, if you are marking correctly, here there are one correct match. That was easy enough in this case. And later is going to ask you more question about the shape. Again, I'm not going to go too deep in this because the idea is to mention other 4 projects at least. And you can keep working. Let me see one more. It's kind of symmetrical structure. I don't see an extended emission. Extended emission is this type of pulse where you have a pulse with a emission that is marked by the computer in the blue region. It is a much obvious example. So I think in this case it's just a symmetrical one. Let's see. Okay, okay. There's one single pulse followed by a signal emission. In this case, correct. One more. We'll connect an emission. And so forth. I forget to, I can mark 2 options actually there, and I missed to mark 1. But you can do like that. And in talk, you can speak about the different subjects, introduce yourself, speak with the science team. Well, sorry, you are seeing an additional forum there that is only for the science team, but don't worry about it. And now the thing that is going to interest people, how you can contribute and be maybe part of the team or maybe part of the paper. Yeah, already by doing classification in any of these projects, you are already participating. All the data you are clicking in the actual workflows. I'll count it the practice one because they are that. They are going to be part of the data that we download for the project, where people have put the different contributions, how they classify into different shapes, uh, there is noise, the shape of the birds, etc., etc. All that is already a contribution that is part of the one of the first data products of every science project. After that, you can contribute more or less depending on the structure of the citizen science project, because in some cases you are going to have additional way to participate, like in super user groups. In other project you are not. You are going to have to see how each project deals with that. In the case of Bush Chaser, was a kind of interesting experiment that was started back in 2020. You can see here the date. We started this in December 2020. And the first iteration of the project was just this. A couple, I don't remember the exact number of people right now, all super users from other projects that were called by Mark Kushner, that is in this moment the officer in charge of citizen science department of NASA. If we want to participate in a new experiment for a project regarding gamma ray boards to see how we can put together something, do a trial run with some data, depending on the result of that, we are going to end up with a universe project that is what I was showing. So the initial iteration of Burst Chaser was basically this, a spreadsheet for a closed group of super users. Then we were classifying data. Let me open this for you. We were classifying light curves using T-side, and trying to see what shapes or birds we were seeing, how they were behaving, if we were able to determine common morphology for them, because there is not even that regarding gamma ray bursts. There is not too much accord in the science community regarding morphology of the bursts. We're working on that. We process all that data that is going to end in a catalog. And after a lot of internal works, we ended with the public project that also passes for a beta phase. That you can also help with that. There is a lot of people that join Zooniverse, opt in to participate of the beta projects. And when a new project is rising, you are going to be able to test the first version of it, uh, work with the data, make feedback for the science team about how the project can be improved before it's officially launched in a main phase in the site. So other thing you have to be to have in consideration when participating in citizen science, be patient, because as you can already see, and I'm going to show another example of that later, things in science can take time. Maybe you are start to collaborate in a project and you are going to start to see the first visible results in a year later, 2 years later, depending on the case. Um, when I'm going to show something where you can keep track of your papers, a side project starting in 2021, the paper was just published this year. Last year, the draft was already sent. They were making some amendments, but it took around 2.5 years to have a paper, and have that paper published took 3 years. So be patient. There are projects when you can maybe get mentioned more quickly. For example, the project where you deal with supernovas, supernova hunter, and similar projects that were existing, where maybe you were the discovery of that particular supernova, and you are going to get a quick mention in those type of projects. But when speaking of papers, things can take some time. So be aware of that. For example, I started this detective in 2014, and our first paper was 2 years later in 2016. So something to take into consideration is that. And how much involved you want to be is going to depend on you, your time, and what you are doing in life. Because we have the student for one side that are participating because they are studying astronomy. We have in the other side retired people. Okay, they are retired, so they have also a lot of time to participate. And we have people like me that we are working in other things, so we destined whatever free time we have to this because it's our passion, but sadly no, not my regular work, for example, in my case. So, and if you have any question in some point, please put in the chat and I will answer, or you can ask for things in the end of the talk. Don't worry about it. So we have already speak about Burst Chaser. Now we are going to move a bit away about black holes and such. We are going to speak about this detective and other two projects that were kind of a byproduct of this, where we are going to deal with things more easy to understand if you want, that are stars and how the planet forms and how we can find about that, and another stellar types of bodies. So this detective is a project that is quite old by now, even if now we are in our current, let's call it tier iteration, because we have one original version of the project that sadly doesn't exist anymore, because was in a previous version of Universe that is deprecated. That site and that platform doesn't exist anymore. But you can find that in the original articles about this detective. And we are now in our kind of tier iteration because we already depleted one of the data source we were using, and we are changing our focus a bit. So what we do in this detective? In this detective, we search, like we say there, for disk around nearby star where planets can form. How we do that? Well, we are going to use the data from the WISE mission, and the other two projects I'm going to speak after this one. They use kind of the same data, kinda, not exactly the same. I'm going to explain that in a bit to detect stars with potential disks using infrared in this case, because speaking about different emissions that a stellar body can give you, infrared is one of those that could be more easy to pick than just a optical wavelength with a traditional telescope. So also the science has evolved a lot, and now with James Webb we are going to have another source of things to deal with. But basically, what NASA WISE mission ended doing in the original mission was to scan the entire sky in different bands of the infrared, and we ended with terabytes of data of the entire sky seen in infrared, and to come with to see what we can find galaxies, stars, and other things. In the case of this detective, the idea was to find planets information or system with planets already present, like our own solar system. Those are more tricky because they emit less infrared compared with a newborn system that is emitting much more infrared emissions. But we ended discovering something very interesting things in between those two stages. And how we do that? Because yes, you have the data. What shape have that data? Image. You can see in part then as an image. But with the issue with the image, we only use in WISE, you are going to be in a difficult position to know for sure what we are seeing, because WISE is a low resolution data product, in the sense that the resolution of the telescope was low if we compare it with, I don't know, 10 stars, for example. The aside of being an optical telescope, you can see very detailed image of the sky, you can see background galaxies, you can see a lot of things very easily in a common Pan-STAR image. While in WISE is not exactly like that. Even more, I can show you how the original WISE data looks, or at least not so much process where we use in the project. You are going to see that the stars in after one point they look kind of fuzzy. That was the issue with the original WISE mission. So how we can discard a false positive in this case? You can do a bit of that with computers. Computer can flag when a source is too extended or surpass or is below certain values, or is there is in the click plane, so you want to avoid that, and so on and so on. But there is a limit to that. That is the ambiguous way that some shape has, and computers are going to discard a lot of data that could be actually good, and you need human eyes to see it. For example, a computer is not going to be able to tell for sure if this is a good candidate or a bad one, maybe with only the shape. You need to feed them with a lot more parameters. So in this detective, our approach was to combine this WISE data with optical data of the same object from different telescopes. In the original project, we were using, for example, very old image in some cases. You can see 1952, 1992 from older surveys that was the data available at that point. We didn't even have Gaia yet in that moment of time. Now we are using newer surveys, of course. So what you're basically going to do here is to watch a flipbook that we call, that is not exactly a video because they are individual image, but you can see moving like it was a video, and classify the subject in several options. That in case of this detective is only T screen. You don't have to worry about a second screen. It's only this, and you are going to mark whatever you are seeing. If the object is moving, if the object is moving in a certain section or is moving across the different image, if the object is not round, if the object will be extended beyond the circle, is speaking about this. Saying that before, you have the field guide and you have the other section of the project where you can see the different details. So don't worry, I am skipping things. All the information is there. It's impossible to summarize that a lot because there is a lot. In this case, for example, it looks kinda not exactly round. Could be two stars. I think this is the case. There are maybe two stars in the image blending. So I'm going to mark also that one because they are inside that circle. And you can move to the next one. I think that was also extended, but again, don't worry, you make mistakes, especially you are starting. When I started with this detective, I didn't know about one third of the astronomical tool we are using now in the project. I learned advanced astronomy basically working in the inside of the guts of these detectives. So you don't have to start the project knowing. You can start like I did, knowing anything, but be patient to learn and such. We have here another image. This looks faint, but as I be faint, I don't see anything weird to be worried about. It's not extended, it's not moving. I don't see another object inside any of the circles, so I can put none of the above and move to the other. Um, this is the basic classification that you do in this detective. This is already making a contribution of the project because this is going to be part of that database that the project generates at the free instance. But in the case of this detective and the other project that we are going to mention, for example, this one could be extended, you have an additional way to announce, hey, I found something very interesting. Maybe you want to look at it. And the advantage of doing that is that we are going to know about that particular subject way before that is just only sleeping in the click data that we are going to reach, but we are going to take maybe years until we finally analyze all that and found your discovery there. So, for example, in the case of this detective, you found a particular star that is interesting. You can go to a form that is in the FAQ. You can find it there and say, "Hey, here I have an interesting star that I marked. For example, I don't see anything weird, but I consider that this could be a disk or a new thing for whatever reason, and you put in some particular data about the subject that is present uh, here or is present when you go, sorry, the mouse is not collaborating, to the toll page, that is a very important section. You can complete this form. For example, it's asking you for the subject number. Let's close this. Here is the subject number. It's ask you about other parameters that are part of the data. This is the call it the metadata. And I will not say every project take advantage of this, but a lot of the projects do. There is a lot of additional information on every subject just waiting for you if you click that information icon. In the case of this detective, we use this to have additional links that the one I was showing you before and a trove of information that can be overwhelming at first, but you are going to deal this with in your own pace, so don't worry about it. We even now added this, that is a new feature that was present in the original project. When we moved to the new platform, it is not working, but and now we are trying to incorporate it again, but this kinda in a beta phase. So, for example, I want to send this star. What data I need? Subject data, subject number, sorry. The WISE ID, that is the thing we use to identify the start in the WISE data. So it makes sense that we use that as a central point. If the object is in Sinbad, it's asking that because it's part of the metadata that you can check as a user. It's not in Sinbad. In this case, it says that no astronomical object found at the current coordinate. So we're going to say no, or you didn't check because maybe you no, I'm not sure. You can put you didn't check. If the object is in Sinbad, it's any reference, but we are searching for. In this case, it was not in Sinbad. It have this can be a bit complicated. It have a parallax in Gaia DR3. Maybe if you are just starting with the project, it's going to be difficult to know what that is meaning, but it's just pointing to an additional resource that you can find. Again, all this is explained in the FAQ and the different sections, the field guide, and so on. This page, to give you a very, very rough summary, is a index of astronomical catalog. So you have an astronomical object that have data about it, you are going to find it here no matter what, even if it's very old. And Gaia DR3 is one of the surveys that we use for the astronomical resolution about movement, distance. So it's asking about this. If the star have a parallax, we can put yes, or you didn't check because you are not sure about that. You can be honest and put, okay, I am not sure how to do this. Put that. It's like you only that. You have also something interesting to comment about, maybe something interesting in the image, something interesting in a reference you cut down, anything you have. You can put your name and you can put your universe ID. So we also can know who you are and maybe contact you if you are going to be part of the paper to ask you want to be a public part of the paper or not. So this is the second step. You can work in this detective to be part of the data products, the papers, and so on, aside of being part of the super user group. Then you can try to join in once we let me see. I was to confirm it was here present. Yeah, here. Once you are familiar with the project and you are interested in contributing even more, you can, for example, send an email to that address and you can jump on and participate in the more internal work of the project that in the case of this detective is taking the shape of, let me zoom this a bit because otherwise it's going to be too small for the screen. That here is when we deal when with the subject sent to this form. This spreadsheet is the result of all the people that is constantly sending new candidates to the form. Steven, that is the director of the project, takes that, make an additional filter, and construct a spreadsheet with the rest of the super users when we jump in and participate, analyzing the details, analyzing if it's truly a good candidate or is bad for whatever reason, and we end up discarding anyway. And is it going to be worth of the follow-up or not? depending or internal betting. As you can see, there is a lot of objects that we ended rejecting, others not. They survived several people betting about them. So there is an object that stir long discussions until we finally settle on something. And this is the next step when you are a super user in this detective. After this, these subjects are going to end in papers, in an observation run, depending on what we are doing with the project. And you are already contributing a lot, and yes, you are going to end in a project, in a paper of the project. Like, let me show the first one that was in 2016 that I was telling about. And the final result, all that is final publishing a paper with your results. So it's a lot of work, a lot of time, and quite some patience that you need. Let me check the chat. We have a question so far? No, no question. Okay. So in the case of this detective, we have a more in-depth look about how the project works and how the super users contribute with that. But again, not every project have super user groups. Sometimes your interaction in some projects, your interaction with the science team is going to be in the talk forums. And only that, in the case of this detective and the other projects I'm going to show you next, we have Google email groups. We participate using that. We have regular video calls. We talk a lot in those calls about the project, what we work on, and such. Again, that is not going to be the same for every project. Every project where your participation is going to be a bit more reduced. That is going to depend on the science team. Now, another project, Backyard World Planet 9. This was the first kinda sister project of this detective that also used the WISE data, but in another completely different way, and not the original WISE data, but the data that comes from the current iteration of the mission that is called NeoWISE. The problem with the WISE mission was to do certain kinds of observation in the infrared, you need the instrument to be um, keeping in a certain temperature using liquid nitrogen. For obvious reason, we cannot go back where WISE is orbiting to refuel that liquid nitrogen. So once that depleted, the main phase of the WISE mission ended because you weren't able to take data in a meaningful way because the quality without the nitrogen was bad in the more delicate wavelengths. But luckily, the scientific community make a very good case about, hey, we still can use WISE as it is without the cryogenic part working in the remaining bands that are available to us to keep scanning the sky and detecting like asteroids, nearby objects that could be moving in our neighborhood, and so on and so forth. Luckily, that was accepted, and since several years ago, WISE is currently working. I don't know how much time it have left, but it's working a lot in these years as NeoWise. And that generated a lot of additional data in another way than we can use for different projects. So, what is the idea behind Planet 9 and what is called like that? Because one of the original ideas from Mark Kushner, because he was the father of this particular one, was to find the mythical Planet 9. There is a theory sustained by some evidence in observations, not direct but indirect observation, about how the dwarf planet in the outer solar system behaves, the Oort cloud, and such. That in theory we should have a planet 9 present in the solar system that explain how the dwarf planets are distributed in the outer celestial system, how the certain things in the Oort cloud behaves, and certain weird things about the orbit of celestial bodies here in the solar system. So far, we are still searching for it. But the idea behind this project was to maybe find it in the Neowise image that are at the same as the detective a flipbook of several images where we tried to make a difference imaging, like when Pluto was discovered, comparing several images of the same patch of the sky to see if something changed. Very roughly, that is how the idea works. Um, for example, we have here another example. You can see here that in the difference between the four images, there is an object that was clearly moving, jumping, while the other things are more or less the same or are subtracted of the image. While in this case, these stars are kinda being um, erased of the picture by the subtraction, while this one is kinda doing a disco ball movement when there is one side in two of the image and the other side in the other image. This is denoting a star that is moving too fast, so the subtraction cannot erase the star, but it's showing that there is certain movement there. That is how the Pluto planet was discovered original. I know there is still a discussion going on about Pluto was a planet or not. Well, currently it's not. It's a dwarf planet. There is people still cranky about it, but it is what it is. So Pluto was basically discovered in the same way, barring the difference between the technology, of course. And basically they were subtracting, comparing one image to other using an instrument called blinker when you have only the two image, one image and the other taken later or earlier, and you were seeing what was changing. And Pluto was discovered like that. What we are trying to do is something similar, uh, but to see if we can find the planet 9. Also, that ended becoming in a search for brown dwarf or another stellar bodies that could be in our local neighborhood, and they're going to be detected like that, by denoting in the subtraction or by being an object that is moving in the field. And why the image look like that is do it like that. First, we are using Neowise. We are applying a filter to that, another pipeline of processing that give the wise image more resolution. And after that, we are creating flipbook where that been subtracted, and we kind of generating this weird movie where, yes, I will admit it's not the easiest thing to the eyes, but has been proven uh, effective so far to find several things. In every project, you can see the results. Site seed projects is very new, of course. And in the case of backyard work, you can see that they already published a lot of results regarding that, sometimes about one or two particular objects, made sometimes about 42, for example, or 34, for example, in this case. So there is a lot to do with this data. Another byproduct that was generated from Planet 9 is this other version, that is called the Backyard Wars, but Cool Neighbors, where the data is treated in another different way, and in my opinion, much easier to the eyes compared with Backyard with Planet 9, where you basically are going to search for things moving in a field in a more easy way for the eyes, because the approach here is different and you are going to searching for particularly brown dwarfs here, not for running 9. So the approach is different. The data was corrected in a different way before being processed, and the end result is kinda different. And Again, more easier to test, at least for me that have a high side problems compared with the other. In both projects, you are already contributing by classifying the data, but in both projects, you can send your more interesting discoveries with a form that is going to ask you different things, of course, because is detect is one thing, cool neighbor is another thing, and backyard works is another thing. So this section is going to need for you already be a bit familiar with the different page and what the data is going to tell you. This over here is again reference to the metadata you can find in every image. So again, be patient. If the project looks interesting, give yourself time, get to know the page, read the FAQ, read the field guides, ask questions in talks, and you can contribute when you feel ready for it. Again, this form I'm going to end in a spreadsheet where the science team take that, ingest that, separate possible false candidate or less than ideal candidates, and generate the additional data that the science team use or the super user use to start to generate internal catalog for internal betting, observation runs, and so on and so forth. Again, be patient. For example, that is my picture, and that in the background was one of the original iteration of this detective. And here you can see some of the people that works in the different projects. How much you are going to work is going to depend on you. Dan, for example, he started like a super user and ended developing a tool that now is recognized by the astronomical community called the WiseView tool. And he just created that original to help the group to process the data. And now that it ended becoming an official tool supported by the Natural Science Museum of the US. So the result of your contribution in citizen science can be wild different or the opportunities. For example, I have travel. I don't know. I forget to put that in a link. Let me see if I have something. For example, me traveling to Casleo to help to do observations, create an important tool. With a bit of patience and a bit of constance, you can end in a lot of places with this. So jump in and have some fun is what I can tell. Any questions so far? Because I kind of get lost when I start to talk. No? Okay. How we communicate, you are maybe asking you, because we do a lot of things, we have a lot of things to deal with, and yes, email and forums are a very nice thing and very vital things to do, but how else we interact with each other and the science team to produce science? Well, I have no problem to show. For example, we conduct a this is just a recording of one of the last call of Shakespeare when we are trying, one of the science team is trying start to develop an internal website to review the data that is started to come from the classifications. So this is going to be something internal probably. And there is nothing in the web, there's just an internal demo that we were using to show things. Uh, Calls, video calls now, especially after the pandemic, become something very, very common. But in the case of citizen science, we were doing these things. I think we started to do the regular video calls in this detective in 2015. And now we do that in this detective. We do that in Backyard Wars. Backyard Wars Planet 9 and Backyard Wars Cool Neighbors are working as the same things internally. So if you join the super user group from Planet 9, you are going to be kind of part of the Cool Neighbors anyway. And the same goes for Bush Chaser, and the same goes for Planet Patrol. That now is going to be also a new project called Eclipsing Patrol. I'm going to show that in a bit. So this is also very important, and also that maybe if you are starting in a new project and that project maybe have calls, but not everybody can join because yes, we are all around the world. Um, you can do what I do. That is one of my way to contribute to the groups. I record these calls, and after that I upload the video, like where you are going to be able to see the talk video later in YouTube in a private way, of course, because this is not public. So everybody in the science team and the super user group can watch the video, even if it's not live, and participate in the discussion if they were not present there. But commonly, we discuss a lot of the main things in this call, so we decide how the site is going to work, what is the next step in the different projects. If we find interesting things to talk about, we deal with the subject or the paper or whatever in that moment, and we ended talking about maybe some of three or four potential interesting stars in two or three calls until we decide about it, and so on and so forth. And that is also very important. Even keeping archives about the projects or the things that they are discussing is a way to contribute. So again, how you can contribute is going to vary widely according to the projects. Same go for I was reading a question about certificates in one point. There are some projects that maybe can give you certificate of participation, but only a few use that. And in the other, you are going to have to wait for a paper to be formed and maybe be part of the author list there. In my case, with some patients, I started with some this detective paper, and I have accumulated around 16 now, where I am co-author of the different papers, the different projects. His Planet Patrol, here is from Backyard Wars, this detective, and so on and so forth, and some secondary things like when I was participating. Let me found it in an asteroid observation. Yes, for example, this that was something local, but was kind of thanks to the citizen science participation. And maybe you are going to be, aside of being a paper, you are maybe going to be part of that exciting discovery. Like in Wiz Detective, we discovered a new class of M stars, or maybe, rather, a new type of this material around some M stars that were not known before. So be patient, again, be patient, and that is going to bear fruit in one point. So, and let me go back. Yeah. So we already speak about Board Chaser, this detective, Backyard Wars Planet 9, and Backyard Wars Cool Neighbors. Mm, how the site works in each case, and how you can participate more or less, depending on your interest, in each of them. No questions so far? Okay. Now, before talking about one of the last, kind of last, not necessarily, but kind of last, for anybody starting in science, city science in particular, and this is a recommendation that we do always, you can create this that is called an ORCID ID. It's a free account, and you can use that to keep track of your contributions, and people is going to know more about you because these papers are used by the community, and they read the author list. They may be going to check on you, and you are going to have your curriculum already presented there in UID to show people, oh, he's participating in this work and this work and this work and this work. So this is a suggestion that I'm going to repeat in this call for everybody participating in citizen science. Create one of these accounts. Is going to be very useful for you, especially if you are a student, to keep track of your work and have, again, send a curriculum about your contribution so far. As you can see, all those green dots are indicate people that have ORCID ID, and it's a very, very useful tool to have when when making an index about your works and where people search for that. This paper, speaking of patients, is a result of a 2 years and a half work and was an internal side project of backyard works. So that is something also interesting that you can end up doing in a citizen science project, because sometimes there is a particular idea that maybe is not good enough for a full-blown citizen science project, but it's interesting to be a work in itself. So you are going to participate like that, but you have to be part of the group. For example, now I'm showing you one of the initial communication from 2021 when the idea for that paper was started. David is one of the scientists behind it, and if you go to the page of the paper, it even have a video where he described. Yes, here when you save YouTube, there is an entire video about this paper that you can watch. Uh, okay, where the cursor go? Ah, there you go. In this case, that paper started as a side project inside my Jaguar. Well, just by email. Okay, I have this idea. We want to answer a particular things about a subgroup or object we have. You are going to participate analyzing this and this data about the subject set that they be started to send to everybody that participate in the side project. And well, after a couple of years, we ended with this paper when we did a census about a few stars and brown dwarf to determine better some characteristics, membership of group, and so on and so forth. Again, there is a lot, and it's very hard to reduce to a 40 minutes talk. So sorry if sometimes maybe I'm jumping things. Again, ask me about, and we can return that. I already see that the article have quite a few downloads. That is a way to measure success when your paper is cited or used by the community. And that is what you hope to see, really. So again, be patient. There is a lot of things to collaborate. There is a lot of different projects and a lot of different science teams. Be patient, and you are going to find your ideal group. That group when you say yes, I belong here and can work with these people, and it's not going to be any feeling of work. You are going to be just contributing in something that you kind of love. So now for the final project that is now currently about to return to the public in a way, that is Planet Patrol. Planet Patrol, if you search for this in Universe, you are going to find it, but the project is without data from some quite time ago. We run the project, we analyze all the data, and we started to generate catalogs. I think the first one, let me see. Yes, the first one, what we did was this one in 2022, was the first catalog, and we have more already. You have the second version here, for example. That was the result of the first iteration, that first paper. This project, after that, continue working in a private way. We using the Google email group, and some internal spreadsheets. And now those spreadsheets ended evolving in a website that we use. Let me put it here. In a website that we use for reviewing the data. We are working in new catalogs for exoplanet transits. Let me a bit. So that site where we were searching for planets using the transit in the light curves. Not every subject is working. And then evolving in an internal group that you have to be a super user to participate. So again, this one is not public right now, but generating a lot of science products about. And now we are returning to the public with this that is just now finished, was 2 weeks ago, and it's a clicks in binary, when instead of dealing with exoplanet transit, we are doing with another secondary data product that we in the public, we went to a something private with the conclusions. We started to evolve and see, okay, we can do this and we can do this, we can do this like this or like that. Oh, also, oh, by the way, we also have this in our data, so okay, maybe it could be an interesting project by itself. Also, kind of what happened with Cool Neighbors. And we ended generating an entire new science citizen science project aside of keep working in the results from the initial one. And Bush Chaser started in the opposite way. It started like a private experiment in the science teams and ended becoming now a public universe project that is currently working. So again, how you can participate in this project is more or less the same way. You can start with the classification. You can go to the talk page, interact more with the science teams, and maybe end up becoming part of the super user groups. Participate more. Let me see a question. That is regarding the call. Okay, okay. Summer camp certification. That is cool. Well, and that gave me the, to mention again, total certificates are not the more common things. I'm going to put here. These type of certificates are not the more common things in the citizen science project of Universe. You usually are going to have to wait for a paper to be generated, but there are a few projects that generate certificate of participation, like the one where you transcribe notes from all astronomers. There is a lot of things you can do in Zooniverse, but yes, certificates of this type are not the more common thing in Zooniverse. There are projects that use them, but again, take that in consideration when you are starting to participate. You want something quick, maybe that's not going to be so easy to obtain. Again, let me go back where we are having pending in my case notes. Okay, we are speaking about this detective or chaser, backyard wars, cool neighbors, Planet Patrol, and the clicks in Binary Patrol now. kinda funny name. Google, I know that I am sharing. Go away. So, okay, since I seen question about that, any questions so far? Please be free to ask about any of the project or something in particular you want to me to do. Okay, so many, I see a comment. So many cities and projects are there, so any project have upper hand over other, or we can choose one as per. Yeah, yeah. You are completely free to jump in whatever project you feel that you want to contribute. The only thing can change from one project to other. There are projects that are for the long run. For example, Planet 9 is in the long run. This detective is running for almost, is running for, sorry, 10 years was in February. This detective is running from the last 10 years. But there is projects that maybe are going to run for a few months. And once the data is depleted there, they are going to, well, just stop and they're going to analyze the data. Maybe you can participate more on them if you are working in the internal data analysis like Planet Patrol. Planet Patrol working for a few months, and after that, all the people that keep working in there are the super users of the projects aside the science team. So go for your liking, the subject that interests you the most. Could be light curves, could be to see actual image like in this detective, or in Cool Neighbors, or in Planet 9. Again, that's going to depend on what you like the most, of light curve that the doctor was showing with the gamma waves, or for example, Planet Hunter test, that is another project I never have enough time to participate, when you can work with the light curve, with the data points of the light curve. So yeah, how much you can contribute is up to you. Okay, thank you, sir. No worry, madam. So yeah, and also it's a very nice way to learn. Again, in my case, I started knowing. Let me go back to this detective where you are. In the original this detective, we were using Sinbad, we were using Vizier, but I didn't have any idea at all of all what all that. I didn't knew what was that. And okay, they give us a very small field guide in that moment. Well, we started to learn with that. From that point on, we started to evolve. We started to evolve the guys. We passed those guys to other users, so they keep learning, and we keep evolving, teaching each other what new things we can improve, so on and so forth. So don't be afraid, don't be overwhelmed. Start with some patience. You are going to have a fun time depending on your interest. So uh, I don't remember how many years back Soban joined this activity. Actually, I'm not going to show that, but I can. I can actually, because I am one of the administrators. I can tell you when Soban joined this detective. Let me see. But thanks to Soban, I am here. Let me see. Soban, where are you? Soban joined this detective back in 2020. So life is life. So okay, we're saying that the time was running up. I don't know if anybody else has another question, or we can start to finish the transmission. So just let me know. Put over here again. As you can see, there is a lot of things to work on Universe, and there is page outside the universe, of course. One of the more known ones that I never had time to participate, I think, is called Galaxy Cruise. I think Soban is participating in that one, but yeah, I never had the time to do that. That is a separate page that is not in Universe. So yes, science. There is a lot of science to be done, and it's going to be each day a bit more. With James Webb already working, we have some very big telescopes about to start working really soon. Um, yeah. Okay. I don't see more questions so far. So yeah. For example, you want to pick me in some of the projects, you are going to find me. You are going to find me over all the projects I were talking about. So I am not so hard to find. Or someone can track me down if you don't know how and ask me questions. So in my case, I relatively easy to find. Not so far. Okay, well, I have my own. Oh, okay. So I hope my talk was good enough and clear enough because there was a lot of things to cover. So I hope that was good. Well, my webcam is on. Well, thank you for having me here. By the way, again, speaking of archives, it's very nice that you have these talks in the archive in the channel because yes, I was seeing the videos of some of the talks because I was unable to see live by time constraints. So it's a archiving is something very important. So people archive everything when you can. Have a nice weekend. But whatever left of the weekend by now.